All right, we're going to switch gears a little bit and talk about another one of Newton's laws. The first law says an object at rest stays at rest. Object motion stays in motion, constant speed, straight line, until acted upon by an unbalanced force. Newton's second law says basically F is equal to m times a. This is Newton's third law that we're going to talk about today. You guys remember what Newton's third law tells us? You guys have learned this before, right? Grade 7 or something? What is it? Yeah, every action, there's an equal and opposite reaction, right? That's probably the easiest of the three laws, right? Because it's pretty straightforward, right? If there's a force of 10 newtons one way, there's a force of 10 newtons the other way. Negative 10 newtons, end up balancing each other, right? Here's object number 1, object number 2. Somebody want to come up here and draw a free body diagram for object number 1 when they collide? Okay, go ahead. All right, go ahead, Nick. So Nick's drawing a force of gravity downwards. Is he correct? Yeah? Yeah, he's good. Okay, the normal force is acting up, and it looks like it's about the same length as FT there, so looks good. Yeah, okay, good. What next? Okay. No, that's not it. Hold on, Nick. We're going to look for the forces acting on car number 1 when they're colliding. So as they collide, what are the forces acting on car number 1? So you got 2 forces there, and that's correct. So far, so good. But we have to draw all of the other forces acting on car number 1 here. Let Nick do it. No, you know what? We won't worry about friction. We'll say we're on ice here. That's why they're wearing helmets, because they're hockey players, right? Okay, so there's a force, we want to call that F12. Okay. Any more forces? Any more forces? What about that Newton's third law that we were just talking about? For every action, there's an equal and opposite reaction. Is there another one? He's drawing the rusties there for lighting green. Is there another force acting? If for every action, there's an equal and opposite reaction. Okay, so draw it. Hold on. Just hold on, Simon. Okay, draw it in. So he's going to say, look, there's F12 going to the right, then the force acting to the left would be F, call it 2-1, equal and opposite. The force of 2-1-1. Yeah, F2-1. Good enough. Yeah, good enough. Good enough. Okay, have a seat. Thank you. Is he good there? Here's the problem with what he just did. And I kind of tricked him into doing it, but look, they cancel out. When these two cars collide, all of the forces cancel out, at least the way that we have it drawn here. What's going to happen if the net force acting on this car is 0 as it's moving towards the other car? Next, it's going to keep moving at the same speed and in the same direction. So when these two cars collide, if this diagram is drawn correctly, when these two cars collide, car number 1 will not change the speed. It will keep moving in a straight line at a constant speed. It'll go right through car number 2, which, of course, does not happen. So there's a flaw in the diagram, and I kind of tricked him into drawing it the way that he did. But there is a flaw with the diagram. And the flaw with the diagram comes from the way that you have learned Newton's third law. That's why I don't like stating Newton's third law the way that you guys just told me. For every action, there's an equal and opposite reaction. It's correct. It's absolutely correct. When your grade 6 teacher, your grade 7 teacher taught it to you, it was correct. But Newton's third law, which everybody thinks in junior high school is the easiest one to understand, I think is actually the hardest one to understand. When we state it the way that you stated it, and there's a good chance, by the way, that a grade 6 teacher didn't completely understand it either. When we state it the way that you stated it in grade 6 or grade 7, it infers, it doesn't say, but it infers that the net force acting on an object is always 0. Because there's a force acting this way, there's always a force that balances it acting the other way. For every action, there's an equal and opposite reaction. But that's not true. There still is an equal and opposite reaction every time, but it's not quite the way that we have it drawn here. Here, let's clear this. I'm not going to draw gravity and the normal force. Even though they're there, Nick, you're right about those. They do balance each other out every single time. But I am going to draw the force on car number 1 here. The force on car number 1 is caused by car number 2. So I'm going to call that F21, right? Car number 2 pushes car number 1 to the left. But car number 1 pushes car number 2 to the right with an equal and opposite force. Notice the difference between the two diagrams that we had and now have. Nick had F21 and F12 drawn on the same object and therefore balancing each other. I have them drawn on 2 separate objects. Do they balance each other now? No, it's like I apply a force of 10 newtons on this desk, Nick applies a force of 10 newtons on that desk. Do those 2 forces balance each other? No, because they're on 2 separate objects. Here's the way that I like to state Newton's third law so that we don't get confused the way that Nick and some other people in the room were confused with that diagram. As opposed to for every action, there's an equal and opposite reaction. Let's say if object A applies a force on object B, then object B applies an equal and opposite force on object A. But listen, for every action, there's an equal and opposite reaction. It's still correct. But this reminds us that we're dealing with 2 separate objects. And therefore, even if they are equal and opposite, they don't balance each other because they're not acting on the same object. Does Newton's third law always hold? Do we always, every single time there's a force acting, do we always have an equal and opposite force acting on the other object? If object A applies a force on object B, does object B always apply a force on object A? I'm not saying most of the time. I'm saying always. Who says yes? I'm saying if object A applies a force on object B, does object B always, without exception, apply a force on object A that's opposite, equal and opposite? Always? Any exceptions to that? Are there exceptions to that? Okay. Give me a situation. Hold on. Yep. Oh, okay. Oh, okay. So a smart car collides with a semi-truck. You're saying that the force on the smart car would be bigger than the force on the semi-truck. Clearly, the smart car is damaged a lot more than the semi-truck is, right? So therefore, there must be a bigger force on the smart car. Okay, that seems to make sense. But hold on for a second. Hold on for a second. No, actually, Newton's third law does hold in that case. Okay, when the smart car is heading towards the semi-truck, maybe the smart car is going really fast, going really slow. Maybe the semi-truck is at rest. Maybe it's moving fast. It doesn't really matter. As the smart car applies a force of, let's say, 100,000 newtons on the semi-truck, the semi-truck will apply an equal and opposite force of 100,000 newtons on the smart car. Now, the semi-truck doesn't get damaged that much. The smart car does. How come? If they're equal and opposite forces, why doesn't the smart car get damaged the same amount as the semi-truck? Why isn't the semi-truck affected as much as the smart car is? Because the smart car is less mass. Good. And it's not as tough. It's not built to be as tough as that semi-truck is. So although it's equal and opposite forces, the smart car can't handle the force like the semi-truck can. Does that make sense? Still equal and opposite forces. All right. So we've debunked that one. That's not an exception. Are there any more exceptions that maybe you can think of that are legitimate exceptions here? Anyone? Yeah, equal and opposite? Okay, so that still obeys Newton's third law. Now, he's affected more by that force. She's saying if I push Isaiah over, and he's not expecting it, but I'm kind of bracing myself, he gets pushed over, I don't go backwards at all because I've braced myself, and there's this force of static friction between my feet and the ground. Those forces still balance. Yeah, they do. Yeah, they do. He's affected more, not so much this time because he's less massive or more massive, but because you've braced yourself and he hasn't. He wasn't expecting it. Okay, Newton's third law still holds then. All right. So 2 for 2 for Newton's third law still holding. Yeah.
Okay, let's say there's a fly in this room.
Yeah.
Flying around.
Yeah.
By me.
Okay.
And then swat him.
Yeah.
The room, and he's dead.
Okay.
And like if my swat had, or if my hand had a force of.
Okay, so I got this straight. You're swatting the fly, and you squish the fly. You're saying it's not applying as big of a force backwards.
So let's say it doesn't squish. Just get hit.
Okay, so you didn't squish it. You just hit the fly, and it gets batted across the room, and your hand isn't even affected by it, right?
Yeah.
Okay, so you're saying by a force of 50 newtons on the bug. All right. Here's the thing. Newton's third law still does apply in that case. It still does because when you apply a force on the bug will always apply the same equal and opposite force back on your hand. The reason you don't feel it so much is because the bug is so light, when you hit it, it actually loses contact with your hand pretty quickly. So the force that you end up applying on the bug actually ends up not being that big. It won't be 50 newtons. You can't apply that force of 50 newtons on the bug because it gets batted out of the way long before the force ever got to be that big. So you end up applying a force of 3 or 4 newtons on the bug. It applies a force of 3 or 4 newtons back on your hand. It gets swatted across the room. Your hand doesn't because your hand is a lot heavier, and kind of like when Cameron pushed Isaiah, you're also kind of bracing yourself with your hand, mainly because it's got more mass, right? Okay, got another one? Isaiah, you got one?
Say like a car.
So Isaac's question is, you're pushing a car from behind with another car. Okay, and you're saying that, let's say we draw a picture of this here. Here's car A. It's you know what this is. You're making fun of the artwork here, but this is like a car that can go in both directions. Like you're on a spinny seat, so you're looking this way, and you want to go the other way, you just flip around and go the other way. It's got headlights on both ends. Okay, it's like ambidextrous car. Ambidextrous car. We should do it so that it can go both ways, actually. Wheels that rotate, so it can go all 4 directions. Anyways, car A, this is let's modify this car a little bit here. Okay, there we go. Now car B is over here. Same kind of car, more or less. Different color. Wheels a little closer together. There we go. Car B is this way. So it's pushing car B forward, right? We're going to say the force of A acting on B is this way, and it's moving, and he's applying that force constantly over a period of 30 seconds as he keeps pushing the car forward. Does car B push back on car A with the same force? Yes. Yes. Why does car B keep remaining? Why does it keep going forward? Or car A, sorry, keep going forward even though there's a force pushing back on it? Well, because whatever force that acts between the wheels and the ground here that's propelling car A forward is not overcome by the force that B pushes back on A. So if B pushes back on A with a force bigger than the force of friction between the ground and car A, then it wouldn't keep going. Then it would slow down and stop. But as long as the force of friction between the ground and car A is bigger than the force of B pushing back on A, it's going to keep going. No, that doesn't. The friction of the tire doesn't have to have the same force at all. That's a completely separate thing. When car A pushes on car B pushes back on car A with the same force every time. Okay? Car B was at rest. Car B is being pushed forward, okay, by car A. Car A already had motion. The only thing that's going to stop that motion is a force that exceeds the force that it has propelling itself forward. Okay? Yeah. squish the bug and you deform it, wouldn't it be not equal and opposite then? All right. So now I'm swatting the bug and the bug squishes. Okay, maybe this is the case, right? When you're actually breaking the object, right? The bug or whatever it is. Maybe this is the case where it's not an equal and opposite balance force here. So I pushed on the bug with a force of 50 newtons. No, probably not with 50 newtons because it would probably squish before that, right? So I'm not actually applying 50 newtons on the bug. Maybe I'm applying 10 newtons on the bug to squish it. Well, when that happens, the bug will still push back on my hand with 10 newtons. Same force as I squished it with. Why doesn't my hand squish? Squish the bug. Why doesn't my hand squish? Because my hand is stronger than the bug was, right? Simple as that. My hand is stronger than the bug was. What about this one? What about this one? Let's say you punch the glass and you first of all, let's not break the glass. Let's just punch the glass and not break it. I apply a force of 50 newtons on the glass applies a force of 50 newtons back on my hand, right? We all agree on that one, right? When the glass doesn't break, we all agree that object A applies a force on B, B applies an equal and opposite force on object A. But now I break the glass. My hand, let's say the breaking strength of the glass, so its maximum force can be applied on it, it's 55 newtons. If I apply a force of 50 newtons, okay, then it applies a force of 50 newtons back on me, and it doesn't break. If I apply a force of 60 newtons, let's say, then does it apply a force of 60 newtons back on me? No. No, oh, we got one now. But hold on. Go ahead, Simon.
Wouldn't it still apply the force back even though you break it?
Yeah.
Because the initial impact, well, when you break the glass, it'll push back against the glass, or you push the glass here.
Yeah. Yeah, here's the thing. When I apply a force on the window, it will, even if it breaks, apply an equal and opposite force back on my hand. Here's the thing, though. If the window breaks when I apply a 55 Newton force, then saying that I'm applying a force of 60 newtons is like, it can't do that. It broke as soon as I applied 55 newtons, right? The glass, when it was breaking, applied a force back of 55 newtons on my hand. I applied a force of 55. It applied a force back of 55 newtons. Why did the glass break and my hand didn't break? Because my hand's stronger than the glass. My hand might have needed 500 newtons to break. The glass only needed 55 newtons to break. What if I throw a rock through that glass and it goes straight through, creates a hole, and then it just keeps going, slows down a little bit, right? But it keeps going through the glass. A bullet goes through glass. Barely even affects the bullet, right? The bullet applies a force on the glass. How much force on the glass? 55 newtons. That's all it took to break the glass. The glass applied a force of 55 newtons back on the bullet. What happened to the bullet? Let's slow down a tiny little bit, but not much, right? Why?
Because it has so much.
Because it was moving so fast. Doesn't mean that we didn't apply an equal and opposite force on it. It just meant that it wasn't affected very much by it. The glass was affected more by the force than the bullet was, or than my hand was. But it's still the equal and opposite force. Here's the thing. Newton's third law says if object A applies a force on object B always applies an equal and opposite force on object A. Always. Zero exceptions. Always. Every single time. We can't have an action force without a reaction force. Go ahead. All right. Let's list a few action-reaction forces here. Now that we know that Newton's third law always holds. Let's say the first action-reaction force is a foot on a soccer ball. So I kick a soccer ball. Who plays soccer here? Okay. I kick a soccer ball. My foot applies a force on the soccer ball, right? Correct? Of course it does. Right, of course. There's no trick to that. My foot applies a force on the soccer ball. Otherwise, the soccer ball wouldn't go anywhere, right? What's the reaction force? If object A applies a force on object B, then object B will apply an equal and opposite force on object A. Make sense? Why does a soccer ball go forward and my foot doesn't go backwards? Well, A, because my foot's heavier, and B, because I was bracing myself and the soccer ball wasn't. It's kind of like pushing Isaiah again, right? How about this one? You ever get up in the middle of the night, got to go to the bathroom, drank 6 bottles of water before bed? Got to pee at 3 in the morning? You're getting up, and your toe kicks the end of the bed. So you're walking across the carpet in the dark room, and you kick the end of the bed, and it hurts. It really, really hurts. Why does it really hurt? Because you kicked the end of the bed? No, because the bed kicked you back. That's why it hurts. Okay? The only thing that you do when you kick the bed is maybe damage the bed. Okay? Your foot cannot be damaged by something you do. Your foot can be damaged by something that gets done back to your foot. So when you kick the bed kicks you back. How about this one? I'm not going to write this one down, but you get in a fight at school. Don't do this, by the way. Okay? Violence is not the solution. Nor is that. So you get in this fight at school, and you punch somebody in the face. And of course, you know that 5 minutes after you punch somebody in the face, you're gonna be sitting in Mr. Staffichuk's office, and she's not gonna be happy. She's gonna say to you, "Why'd you do that? Like he didn't do anything. Like you punched him in the face. He didn't defend himself. He didn't do anything to deserve it. And like, what were you thinking?" And your response to Mr. Staffichuk is, "Well, wait a second. Like he didn't do." No, he didn't. There's witnesses. Nobody saw him punch you. Okay, everybody saw you punch him. Nobody saw him punch you. And you say quite legitimately. You say, "Yeah, but at the exact same time as my hand punched his face punched my hand back. So I didn't do it first. We did it at exactly the same time." Hand punches face punches hands. Got it? If object A applies the force on object B applies an equal and opposite force on object A. All right, guys, let's quickly do a little bit of a math problem involving this, and then we'll wrap it up there, okay? So here's the example. Mr. Dickie's mass is 70 kilograms. Who do you want to pick as an example here? Okay, Isaiah. Isaiah, how do you spell your name? I-S-A-A? There's a lot of vowels in that. Okay. Isaiah, what's your mass? What are you in pounds? 180, so you're probably going to be, what is that? Maybe, no, it's more like 90 kilograms, let's say. Yeah, I'll say 90 kilograms. Isaiah pushes Mr. Dickey, causing him to accelerate at 2.5 meters per second squared. What is Isaiah's acceleration? Do you think Isaiah is going to accelerate more or less than me? How come? But wait a sec. If Isaiah applies a force on me, then I apply an equal and opposite force on him.
But it's mass times acceleration.
So if he has more mass, he's going to have less acceleration because he has, with the same force, more mass, less acceleration. All right, let's set this up. Let's say the force of 1 acting on 2 is equal to the force of 2 acting on 1, but it's opposite in direction. So let's say M2 times A2 is equal to negative M1 times A1. So the mass of object 2 times the acceleration of object 2 is equal to negative M1 A1. mass of object 2 doesn't matter which guy is which, right? We'll say that, let's say that I'm object 2. So my mass is 70 kilograms. My acceleration is 2.5 meters per second squared. Isaiah's mass is 90 kilograms. His acceleration is A1. We do that math, and it looks like A is equal to negative 1.9 meters per second squared. Does Isaiah accelerate less than me? Yes, because he's heavier. Same force, bigger mass, smaller acceleration. So we're now tying together two of Newton's laws, right? Newton's third law says the forces in that interaction have got to be the same. Newton's second law says that the acceleration won't be the same, or the effect of the force won't be the same, because one guy happens to be heavier than the other guy. Make sense? All right. You got one homework question? Actually, no, you don't. You have your quiz tomorrow on multi-force problems with free body diagrams, and of course your lab is due tomorrow as well.